Okay, welcome everybody. Thanks for being here and remote. It's nice to be back. I haven't been in a live colloquium for almost 2 years or something. So it's good for me to be here. So I missed the first part of this talk. So our speaker today is Chris Curtis from the Math and Stats department. So Chris comes from a PhD in Washington and a postdoc in Boulder. He's been with us for 9 or so years. He's a very active member of the department. He is very much interested in dynamical systems, in extended dynamical systems. He has worked a lot on fluid problems. And he's also quite interested in the type of work he's going to be talking to us about, that is extracting some information from dynamical systems, in this case, spatial temporal systems, I believe, that gives you some sort of idea of what happened in the system without a priori knowledge of what the dynamical system, even if you don't have equations of motion. So Chris is going to talk about the dynamic multi-composition in dynamical systems, multiple scales, multiple missing scales. So thank you, Chris.
Yeah, sure. Thank you. Very nice introduction. Appreciate it. So yeah, picking up where we left off last December, there's some changes. All the work I'm going to be talking about is really primarily work with my PhD student Jay. Though his co-advisor at UC Irvine, Alex, has definitely given us some helpful techniques and hints along the way. So happy to recognize his contributions. I'm going to nominally assume people kind of vaguely remember what I talked about a couple months ago. So I'll skip over some of the initial plug graphs that are just there for eye candy. And again, just kind of remind you, one of the real overall point here is, so again, we're going to be talking about multidimensional time series. In this case, for most of the talk, we're really going to be talking about very real sets of data, proper, honest-to-God measurements that real scientists take, right? And then what do we need to do to understand how to potentially model those without necessarily making recourse to first principle physics models. And as we'll kind of quickly see in the problem domains we're interested in, first principle physics models, while they do exist, are not kind things to work with. They're not straightforward. So there really is some clear impetus to try and have what you would say are equation-free modeling techniques to get things really moving. So I'll just get going because I don't have to keep repeating all the things I just said a little bit ago. But just as kind of a quick refresher of the overall theory that we're going to be sort of falling back on to get our things to go, right? So the idea is, we have some underlying dynamical system. We may not know what it is, but we know it's there, at least in principle, right? And affiliated with said dynamical system in its initial condition, we have a flow map. And once we have said flow map or any other observable, we might want to tack on to our data that comes from our dynamical system, right? Say tracking temperature and fluid flows, what have you, right? We can think of any observable along the flow as really the result of the action of a linear operator, i.e. the Koopman operator on that observable. And the definition of the Koopman operator, again, really doesn't come from anything but this just basic identity, right? So frankly, at this level, honestly, as you probably might remember me ranting about last December, it's almost a little goofy. It's just notational, right? And it really, frankly, hides the fact of how complex flow maps can really be. But it's nice to say that there's a linear representation of it, right? Because if we have linear representations, then we get to think about using linear operator techniques. In particular, we really get to think about, okay, but what if we had eigenvalues and eigenmodes, right? That should tell me something. Yeah.
So Chris, if it's linear and the system, original system is non-linear, that means that you're just locally looking in space or locally looking in time?
No, not necessarily, right? It really is, you are re-encoding, right? All of the properties of the flow map, right? Now, instead of thinking of just arbitrary observable tracked over flow map, you're thinking, no, there's this space of observables acted upon by this affiliated map? What are the properties of that linear operator? So you're really trading any finite dimensional advantage here up to an infinite dimensional analysis problem here, with the only perk being you picked up a linear operator to do your infinite dimensional analysis. So you're really saying, okay, I could try and solve the differential equation exactly, or in some sense, I could study the behavior of every possible observable over the flow. And that should, in some sense, give me equivalent amounts of information, right? Roughly speaking. But again, there's nothing deeper to Koopman's initial definition than just this cute little rewrite. And yes, if you do that cute little rewrite, it just so happens to actually be a linear operator. And then once we have that, we can say, okay, can we diagonalize it, right? Which is to say, can we find spectra? And if that is possible, then ostensibly I can write any observable as a linear combination over my eigenmodes. And furthermore, all of the time dynamics of tracking my observables along the flow come down to just temporally updating my eigenvalues. Right? Now, this, of course, ducks out over a range of technical questions having to do with continuous spectra, what spaces are we in, and all of that good stuff. And to some extent, there really aren't good answers to those questions right now in the literature, so we just duck them completely. Okay. And this is more of just a rehash of a very similar thing. I mean, I guess the one nice thing about thinking about infinitesimal generators here is that they do allow us to think about our eigenmodes and eigenvalues as things independent of time, just relative to an autonomous dynamical system. But again, all we're really doing here is just shuffling terms in one way or another, right? This doesn't get to the fundamental problem of, if you're so obsessed with finding these lambdas and phis, how do we get out of it? And so that's where we're going to, motivated by, right, we want this to be a data analysis technique. We say, okay, but if I've got measurements, and in particular the fundamental time series affiliated with my dynamical system, then with that in place, whatever the Koopman operator is, I know it needs to act like this. It needs to keep me going from one time step to the next. And once I have that fundamental identity in mind, right, I can take my time series, split it up into two pieces, a step back, a step forward, and then say, okay, if I'm really interested in linear operators, then let me just find some linear operator, in this case a matrix, that gets me from a step back to a step forward, right? So at the end of the day, you reduce everything down to a pretty straightforward regression problem. And this regression problem is so nice it has a closed form solution for the matrix K that's your optimizer. And everything can be dealt with here with very standard techniques for numerical linear algebra, right? This is just SVDs, call your favorite, you know, eigenvector routine from MATLAB. I mean, it's a handful of lines of code. It's super straightforward, right? And so the moral of the story is, to data, we find our fit matrix K naught, right? Closed form, diagonalize it, and then the eigenvectors in V serve as approximations to our Koopman modes. The eigenvalues in T serve as approximations to our Koopman eigenvalues, right? Yeah.
So Chris, in this case, your vectors Y are supposed to be
Matrices.
matrices because it's space and then time runs around.
Roughly, yeah.
They have to be long in time, so to capture all the dynamics of the dynamical system.
Ostensibly, yeah.
So you're assuming some sort of equidicity of the system somehow.
You have
stationarity of the system.
You absolutely can do those things, and if you do those things, I'll say a lot of the work out of Igor Mezik's group at Santa Barbara, that's when you can actually finally start proving some things in terms of like, yes, this method should converge in infinite limits, et cetera, et cetera, et cetera. And if you actually want to get any real concrete information around the behavior of your Koopman operator before you actually just slap this kind of hand-wavy, right, numerical approximation scheme at it, you need to assume something like the ergodic hypothesis, right? Because the ergodic hypothesis necessarily makes this a unitary matrix, and now we're sorry, operator, and now we have all these nice things we know about it, and then we can take limits, et cetera, et cetera, et cetera. Yeah.
So are you also making the assumption that the linear operator is constant over time?
No.
Yeah, okay. So the matrices there, was that just for one time sample? Or
Sorta. So the nice thing here is, right, because of this underlying semi-group structure, right, we can sort of get time to just become a parameter, right, acting on the affiliated generator. And the impact of that is our eigenmodes stay fixed in time, right? And to move our self forward in time, we just update our eigenvalues and exponentiate. Said another way, if I want to run my numerical approximation scheme forward in time, I just look at powers of k naught, and that moves me across time steps. Yep. So it's kind of constant. So anyway, that's all the really nice, pretty story. And now let's get into the mess. And you can tell I'm having more fun because my titles get more, whimsical. Anyway, that's how you know I'm in a good mood, whimsical titles, right? So my PhD student Jay works for NIWIC, specifically in their atmospheric modeling division with a focus on understanding how bouncing radar off the sky is a good or a bad idea and how we can make that better or worse. And so that means we need to understand something about measuring and then modeling dynamics in the ionosphere. And now the thing about the ionosphere is it is just goddamn massive. Aside from the fact that it spans around the globe, it runs over about 200 to 300 kilometers of vertical height. And you'll note the figure I got here is very handy, right? Here's the world of airplanes and mountains, balloons, intercontinental ballistic missiles, space shuttle, for scale. Anyway.
That's linear.
What's that?
That's a linear scale.
Roughly speaking, yeah. We aren't, no, we're not on powers of 10 here. Good point.
No, because otherwise everything will look close or far.
Yeah. So anyway, moral of the story, what we have here is something that basically starts just a bit above where we have weather, right, and goes all the way out to space. It is a comically complicated world of ionized gases or plasmas, right? Sun-forced chemistry, and then any number of different sub-problems in electrodynamics to boot, right? It just could not be more intricate. Moreover, if we're talking about bouncing radar off of it, we've added a scattering problem into boot, okay? So certainly there are physics-based models out there. Jay can kind of speak a little bit to how good or bad or old or young a lot of those are. Any quick thoughts on that?
They're very complicated. They take a lot of computing. But they can be accurate if you have the right initial.
Okay. So they're there and they can be useful, but they're not easy to use. I assume it takes serious specialists to actually get them.
PhDs.
Sure. Which kind of makes sense. So, I mean, it's not that the ionospheric modeling community doesn't have a response to this. They have been building empirical models that just work with, given measured data for generations. In particular, and we'll talk about this as kind of a rough standard, the International Reference Ionosphere Model. But the thing about those is that, again, they're built on the back of decades of data collected globally. This is in of itself a major problem of just getting it all together, getting your data scrubbed on comparable scales, et cetera, et cetera, et cetera, et cetera. So it's not trivial to build out the RII either. It's just much, much easier to use and interpret. So then, a natural question following up on all of this is, can we do as much or more with significantly less? With less understanding of the physics, because, I mean, you go pull any book on astrophysics off the shelf and it's about 800 pages long. And it is a tour de force of fluid mechanics, electrodynamics, et cetera. And then similarly, just the raw amount of information processing that goes into IRI, doesn't make this entirely trivial either. Okay. So what can we do that kind of gets away from either one of those constraints? And just to kind of give you an idea of what we're dealing with here, the data we're going to be working with comes from vertical sounders. This one is in Boulder, Colorado, and it's pretty straightforward. It's just, some station, it shoots a beam of radar straight up into the sky, right? And then it gets scattered back, and then from the scatter back, it's able, right, to estimate plasma density, right, going up above one fixed location in space. So we get some idea, at least relative to one point, right, one station, of what the plasma density in the ionosphere above that station point is, going from about 100 to 300 kilometers or so. Okay. Moving forward in time. And so this is from 2013 over about a month, and this is sampled about every 15 minutes, give or take. And so there's some things that immediately pop out, right? Day and night, absolutely, right? But then you can likewise see strong variations in plasma density as we move up the vertical column. And again, I don't know how that looks to you sitting out there, but from here you can clearly see all kinds of jagged little noise and flurries and this and that, right, peppered throughout your data set. So these are not clean, tidy data sets. And Jay and I spent months trying to take basic techniques and get them to work, and we'll just watch them fail one after another. This is mean. And
because
what we
the
find,
data is contaminated, or is because
No,
the system
it's-
is so complex?
it's just so goddamn complicated. So a really good way to see that complexity is, so if we look at about 250 kilometers up and just take a slice across time, we're able to compute what's called a Hilbert spectrum affiliated with that vertical slice. And the Hilbert spectrum is best understood as sort of an instantaneous Fourier transform. Okay? And so, for example, what you're then able to see is you have this one frequency way low down, right? And that's day, night, day, night, day, night, right? Diurnal variation. And then after that, you just see this slew, right, of instantaneous frequencies, little micro, I don't mean microwaves, but little microwaves, right? Just tearing through the system in what is essentially a stochastic manner, right? So yeah, it's just that vicious, right?
So that's where your title comes in about the multiple scales.
Yeah, absolutely.
Yeah, it's akin to like trying to model the ocean, like sitting on the ocean floor and looking at just the ripples on like a very small patch of ocean. So there's all kinds of tidal forcing and stuff that can cause these ripples coming through, and you just don't see it until it pops up.
Yeah. And when we start looking at some of the data in a little more granular detail, you'll kind of see how much variation can really kick up. And so really this became a very, very long tail about how do we get DMD to work when you really do have proper multiple scale features just tearing through your system. Because it turns out if you're not clever about it, it'll just rip it apart. So, our time series is a multi-scale beast with significant future variation of both space and time. Now, that said, thankfully I have Jerome Gilles next door to me. My office, his office next to mine, right? Who's spent his entire career basically, showing wavelets are the weapon of choice when you have multi-scale features and you need to actually try and figure out how to tease those multi-scales apart. That's where wavelets just absolutely shine, or perhaps more generally, we can think of it just as multi-resolution analysis. Although Jay and I never go beyond the level of just using basic wavelet implementations out of MATLAB and Python. And Jerome has been absolutely delightful in answering all of our ridiculous questions. Thank you. So anyway, let me give you a really, just in case you haven't seen this sort of thing before, I'm sure Jerome will find something wrong here. There's just no way around that, that's fine. Discrete wavelet analysis begins with the idea of a scaling function of a sum Hilbert space, where everything is going to be done relative to a fixed time scale. For us, that's that 15-minute sample rate. We can't go faster than that, right? And so everything else we do in terms of scales is going to be longer than that 15-minute cycle. Right? Or whatever, right, that limitation is in your data. And then honestly, wavelets are really pretty in the sense that they start with just such a beautiful idea, like take an appropriately chosen scaling function, move it around in time in such a way that you basically get an orthonormal set out. And there's ways to ensure that you do such things, right? Generate an affiliated subspace, and then from your subspace, start breaking it into pieces where the pieces represent longer scales. Here we pick a factor of 2 because that's just the easiest thing to do. You don't have to do it that way. It can be much more general, right? But the moral of the story is you start thinking about everything on fastest scale as effectively slower ones and then details at the fast scale. And then you can just keep iterating this as far as you want to go to keep teasing out longer time scale features, right? Because that's the way we use. And so moral of the story, whether or not that in of itself makes a lot of sense, what we're really doing is saying, okay, we're going to take our given time series, multi-scale beast that it is, and break it out across different detail levels. So all of these boldface Ds are the same vertical number of dimensions as Y. So we're still, right, going over the same heights, but now they are, right, relative to Y in its totality, scale separated in time. And I think J is slowest and level is fastest, the way we have this set up. So moral of the story, all we've really done here is found a systematic and mathematically rigorous way to run through our data and say, here's the slowest stuff, a little less slow, a little less faster. Okay?
How do you know where to cut in terms of how many scales? Because you go like 2, 8, 4, 8. 6.
Yeah, so I mean, I think we sort of purposely make sure to like try and get as close to a power of 2 as we can, so it's just cleaner. And but I mean, in some sense, MATLAB is now set up in such a way, or Python equivalently. All of these like, you know, hanging little bits off the side and stuff, it'll just take care of that. So, you know, you just kind of say this, it gives you that, and then you have to make sure you know how to kind of put it back together again. But you don't really have to lose too much sleep over things like that. Thank you, modern era. I'm really glad we weren't doing this in the 90s. Anyway, okay. So moral of the story, we can separate across scales. And this gives us a way then to sort of reorganize our time series scale by scale by scale. Okay, cool. Now that we've done that, what are we going to do with it, right? And this is kind of one of our big tweaks to the whole DMD paradigm, right? So the point of separating across scales is once you know something about multi-scale systems, right? Some scales talk to each other more than others, right? And DMD, for as handy and in some ways as theoretically elegant as it is also sort of boneheadedly dumb, right? Forward, back, fit. That's it. That's all you get, right? So it's beautiful in its elegance and its application, but from the point of view of thinking about, you know, non-stationary time series and statistics or dynamical systems, it's just ruthlessly basic, right? And there's some perks to that, closed form solutions, blah, 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 but it's also not horribly flexible. So when you think about that for a second, you're like, okay, if I have these different time scales, that means I can also go and ask, what are the correlations among those time scales? Which time scales actually talk to each other more than others, right? And if two time scales really aren't talking to each other terribly much, if they're very weakly correlated, why would I try and slap a linear fit between them? That's not probably terribly bright. Yep. So once we kind of wrapped our head around that, we were like, oh, okay. So what you want to do is run through your different scales, and for the data set that I showed you earlier, we end up with about 11. And then look at the correlations among those different scales, right? And say, okay, some of these clearly talk a lot to each other, and these are my slower scales, right? So this is basically everything more immediately forced by, right, day-night variation of sunlight, right? That's your longest scale, so it's 24-hour cycles, right? And then a few attendant things probably going on the order of 12 hours, 6 hours, etc. Right? But by the time you're starting to talk about 10, 15 minutes, right, that has nothing to do with what's going down here. And you should not try and put one master linear fit that somehow tries to connect all of them at once. I mean, if nothing else, honestly, by the time you get down to your 15-minute cycle time, you're looking as much at noise, right, as anything else. And it really probably has nothing to do with any underlying dynamical system. So at a minimum, we're also just putting a basic denoising technique in here, right, in a somewhat consistent way. So what we do is we say, okay, here's my correlation matrix. set a threshold, and we played with different thresholds, and this one just generally seemed to be the best. And that's going to give me an affiliated graph, right, of people within, right, a connected component, and then folks in different connected components. Okay. And the ones that are reasonably well correlated to each other, we use one DMD approximation here, we use a different one here, and so on and so forth, right? So we are not trying to slap one master linear fit across all these different, arguably very decorrelated scales, right? So every scale gets its own DMD operator because frankly, it should probably be thought of as its own independent entity.
Do you have an idea of the separation between the two larger groups when it comes to the physics?
No, that's actually a really good question. We spent a lot of time trying to stare at it and poke and this and I mean, yeah, like again, everything down here is a little easier because you're like, well, the sun, right? That's pretty plain. After that,
the very deep blue dot that you have there is very telling that it's
completely disconnected. Yeah, absolutely.
Yeah, it's not that it's like coloration. It's like, well, if you go up, it's like coloration, but just if you look at it from the bottom right, it's like, oh, really dark.
Yeah, and I mean, again, there's some idea of like, yeah, on these fastest scales, you're looking at random bits of wind, slight fluctuations and, you know, solar flare counts that day. I mean, there's just so many different things. I mean, again, because we're crossing so many vertical scales here, the chemistry changes. I mean, that's why you have these, right, different distinct layers in the ionosphere, right? The chemistry of the air is categorically different. And you get different, for example, ionization properties of hydrogen, right, based on the way that UV radiation is getting absorbed and scattered out these different, right, strata. And so
you're talking about two groups that are working different physics and different strata.
Yeah.
Very different physics.
Yeah,
very
absolutely.
different atomic elements that we are dealing with.
Yeah, and then there's boundary layers between them and mixing and turbulence and all the bits. All of it, you know what I mean? So, I mean, at some point, I mean, you're asking a really wonderful question, and a natural follow-up, hopefully someday we'll be able to get to, is actually seeing how much of this is telling us something about those multi-layer structures. But that is definitely future work. I could see Jay shivering in fear because it's scary, but it's a good question, right? And I mean, that's a lot of hard physics. You get these attended inference results, and then you kind of back out, oh, that's this and that's that, and here's why, and so on and so forth. That's how the sausage gets made. So, just so you kind of get a feel of what this does, right, when we break up across these, right, different connected components in our graph after we do our thresholding and our correlation matrix, it does about what you should expect, right? Relatively mid-tempo speeds, everything gets a lot faster. By the time we get out to, right, these guys up here, you're just looking at chatter, right? Essentially noise. And if you want to go back and look at autocorrelations here, you get effectively delta function like spikes. So by the time we're out here, even including this in any of our future like decompositions is kind of silly. It's essentially purely stochastic. Yeah.
So does that noise have something to do with the physics of the ionosphere, or does it arise from other sources of this?
You got me. I just did the math.
Just keep up. That's a standard.
How could anyone look at me of all people and be like, give him expensive equipment? No one thinks that. I have gone out of my way to do two things. Sorry, three. Not become dean, chair, or responsible for high-end gear. Look at me. No dean, no chair, no gear. Just give me a computer and paper and leave me alone, for God's sakes. And people still don't understand that much. I digress. Okay. So the last bit, and in some sense, the one bit of really good, clean physics that was finally necessary for us to get this, and it's embarrassing how long it took us to finally think this up. We fought over this. We fought with the problem for months until we were finally like, and it was a senior guy at NIWIC Doug, who just, I think offhandedly was like, well, yeah, and of course, every 24 hours, the system basically resets itself. There's no memory day over day for the most part of the ionosphere. I mean, there probably is, but it is such a weak effect, right? And so again, this goes back to really kind of understanding the problem on some level. It is one thing to ask DMD in its linear fit stupidity to try and cover a whole month, right? Time step to time step to time step, right? That's brutal because what's happening across here, and you can even kind of see it, there's still enough variation even on the slower scales because you have relatively rare events. You have spikes in the plasma density that just come because someone probably gave someone like me expensive gear and we didn't know what to do with it. We probably wasted a fair amount of the government's money. But anyway,
you have an obvious one, the seasons, the yearly seasons.
we have yearly seasons, but we only have a month of data here. But you're right, if we want to start looking at more interesting, longer term trends, we're going to have to think about that. For us, we were just like, oh, just average over 24 hours. So just take this whole chunk and bust it down day by day and then average across that, separate that 24-hour mean out from the fluctuations, and then do all of our analysis or multi-scale, and then likewise DMD decompositions on that 24-hour
So
average.
you simplify your basis and then you multiply your state vectors, the amount of data by 20 something as well. So it's really advantageous.
Yeah, exactly. But again, it's one of those like really boneheaded moments where you learn all this theory and you're learning wavelets and doing this and you're doing that and you're like, oh yeah, the sun comes up and goes down every 24 hours. And the whole thing just starts over again. Maybe don't try and build models that work for arbitrarily long time scales that don't take that into account. You know what I mean? So just a bit of cautionary warning when you go out as a mathematician. Right? Try and actually talk to someone who does it and they're like, oh, by the way, 24
We are
hours.
in our offices, we have the light on, we don't care if it's day or night.
I don't know what day or night. Do I look like I know what day or night is? I don't.
Dressed in black. For
Right.
a matter you sleep with that thing.
Right. Right. How can I understand 24 hours? It means nothing to me, but it does mean something to the ionosphere. So anyway, right, once we figured that out, everything just kind of snapped. It really was remarkable. Months of just frustration and then everything was just like, boom. Let me show you what I mean. So here's the data, and we do DMD or modeling, if you will, up to the first 20 days of data, and then after that we predict. So we actually just let our DMD model run and see how well we do. And so what we can see down here is, aside from not being able to capture maybe some of the like nastiest little squiggly lines, right? We pretty much otherwise nail the entire time series, right?
You completely confused me now. You said that there is a reset every 24 hours and now you're doing prediction.
Well, sorry, I can take my given 24-hour and then just sort of repeat it day after day.
But this is
And
an
then-
average, it's not really a prediction.
So I average to build out a data set to build my DMD model, and then I run my DMD model from that average. And that lets me recreate whatever time point I want.
So from day 20 to 24, you could not exchange those days. 21 and 22 will not be able to be exchanged.
No. Because this, I mean, so out here, I'm actually running my model out past where I have data. So I take these 20 days, build my average out of that 20, right? So that gets me one average 24-hour window of time relative to the 20 I have to work with, right? Build my DMD model from there, but then once I have my DMD model, T is just a parameter. I can make time whatever I want. So I can run it forward, right, as far as I want,
Okay, so
scaling appropriately.
It was to build your 24 hours templates,
Yeah.
and not to forward in time after one day. That's taken care by the DMD.
Yes. And that's what we're seeing out here. So it actually has predictive potential. I mean, granted, we already know the answer, so, you know, that's nice, but the thing to keep in mind here, and let's hang out with this, although that is a little small. Let me see if I can blow it.
Measures of prediction quality.
Yeah, so right now, probably not terribly sophisticated ones. We did try and get into modeling the variance and then trying to see if we could actually build confidence intervals around our estimates for the average. That eludes us right now. That's a longer term project. Because getting into how to model the variances in the right way and what distributions are we going to start taking things from, it's non-trivial and highly nonlinear, right? So Gaussianity is not going to save you here, right? So moral of the story, this is, the blue line is our model, right? Red is the actual data, and then we're looking at 350 kilometers up, 300, so we're coming down right to the ground here, right? So pound for pound, and again, keep in mind, the red data is just raw. It's not averaged, it's not anything, right? It's just direct measurement, right? So our blue propagating average model, right, is able clearly to capture the vast majority of what we want to describe, aside from when you start getting into higher altitudes, right, these clear, right, kind of rare events, right, that would otherwise send our DMD model flying. Right? We're able to kind of around them. And Ricardo's about to ask a question, I can tell.
I don't know if I want to.
Okay, later.
Okay.
Look, I haven't asked questions for 2 years.
No, it's fine.
You throw questions now.
No, it's fine, man. It's fine. It's a Friday afternoon. It's more fun to sit here and talk about it than just drone on. Okay. Yeah. And so again, that was really the secret sauce of averaging down over 24-hour windows of time. All of that is to deal with these little beasts that would otherwise just send you off, right? Thinking that you're trying to fit to them, right? Point to point to point. And so the averaging over that 24-hour period of time is really about basically figuring out how to tell who is really a part of my data set and who are outliers, right? So that's really what it comes down to. And that's why it works so well. And then you can tell by the time I get to lower altitudes, it's just really not a problem at all. But the physics isn't as complicated, things are more straightforward, right? So that's nice. In terms of some degree of, I mean, again, we don't have things like confidence intervals, but we can talk about, and honestly, Jay should be the one to better explain that. I'm going to defer to him in an instant if someone asks a question about this. So the moral of the story is we can say, okay, let's take our model. That's the blue SSDMD. IRI, if you remember at the beginning of the talk, right, was this kind of international empirical, like international standard empirical model, right, for modeling the ionosphere. And we can also just do something really, really goofy and just take a daily average and then say, you know what, let's our model be just literally that daily average moving forward in time. So just repeat the daily average literally day after day after day, right? And so you can look across height, look across time, average error over time in the 3 different approaches. And then radio people like this. The error is on the horizontal axis here, measured as plasma frequency. I don't goddamn know why. But that's what they want. And we're trying to submit to space weather, so that's what we're doing.
More to the right is more error.
Yeah. Yeah, I'll let you stare at it first. I had to stare at this for like a good 15 minutes. Jay was like, you don't get it? I'm like, no.
And by the way, this answers my question that I did not ask.
Oh, okay.
But just better wait one slide and
No, it's
some
fine.
of my questions will be answered.
So this error is an error in predicted plasma frequency? That's how to interpret it.
Yeah.
So why is this IRI look crappy?
Jay?
It's basically a monthly mean. It's built off of like 40 some odd years of data. And it just predicts sort of what you're not going to get a whole lot of variance over a given month of predictions.
But what is worrying is that the daily mean does better than that model.
Yeah. Not better than our model.
No, that's the good thing is that yours is to the left, but that's on the train.
Well, wait a minute, on the testing, it's doing better than your model.
Well, it's at some heights, not all heights. Not at all heights. No, I mean, and again, this is also getting into questions of like, what do you need to know and what are you trying to do? I mean, to some extent, right, the idea that all of them are able to kind of hang out reasonably well at most of the altitudes that anyone wants to actually get anything done, right? And I mean, in some sense, you can even kind of see, right, like that's probably why RI is still around. It's not around because of this, right? Nobody wants that. And nobody really wants this flying off the way that it does either. So in some sense, by the time it's all said and done, right now, the best we can say is probably where things are most relevant. We're certainly in the ballpark. Now, that said, we're in the ballpark using one data set, not 40 years of information gathered over global measurement sets, right? We're taking from one sounding station.
So that reflects the long.
I think so. I think so. For someone who otherwise doesn't understand how the sun works, yes. Very happy about this. Jay was happy and Jay's radio people were happy. So everyone's happy. We'll see what space weather says. They're probably not going to be happy.
Yeah, I mean, the reason why plasma frequency is usually given, so we want to evaluate it is because the plasma frequency tells you roughly what frequency of radio wave is going to be reflected at a given height. So if the plasma frequency is 8 megahertz at the F2 layer up in around 250 kilometers, roughly an 8 megahertz signal will reflect on that height.
So this plasma frequency error,
Yes.
it's not measured relative to.
So that's the delta between what our model output and what the observations of the plasma frequency.
But if the plasma frequency were 50 megahertz, it would be much larger error relative to the center of the band than if it were 300 megahertz. Is that, am I interpreting that correctly?
Yeah, there's
an error.
this is absolutely. And there's some question of doing some relative measurement probably.
Yeah, it's mean absolute error. Okay. Mean in time.
But still, we're doing pretty well. Yeah. So that's kind of the most applied side of what I've been up to. Let me switch over real quick, see if I can. Chat a little bit about theory real quick. I had to give a few different versions. Wait, no, come on. Wait, why didn't it open up in? That's annoying. There we go. So that's multiple scales. Let's talk about missing scales finally. And I'll probably just gloss over this because it's Friday, it's 4:15. I'm not making anyone stay late for this. And this is honestly getting into just like pure physics. And I love it, but people could be forgiven for not knowing what this is about. So a fundamental problem, all that said in StatMech, is, right, at the end of the day, we kind of tend to think of everything in terms of Hamiltonians representing the total energy in our system. And then what makes statistical mechanics such a nightmarish subject is, right, you know deep down that you really have this fundamental separation of scales. This is still a multiple scales problem. It is. Right, you have this fundamental separation of scales in your system such that there are things that are happening on very, very fast scales and things that are happening on very, very slow scales, right? And we even understand this, right? Like when we talk about equilibrium, right, in thermodynamic systems, right, when we talk about thermodynamic equilibrium, that is radically longer in terms of its time scales than the actual like individual motion of atoms, right, in a given problem, right? For example. Similarly, right, flip side, if we want to think about statistical mechanical interpretations of problems in fluid dynamics and we think about things in, say, for example, turbulence, right, we have wide separations in scales, right, where we have readily measurable things on relatively long scales and then things we can only kind of hopefully infer or pretend we understand on the very, very small scales, right? And that can be manifested in both space and time, although in this problem, we'll talk about everything relative to time. Okay. So moral of story, we want averaging techniques, we want methodology that reduces our problems over the fast down to the slow, right? Because generally speaking, we imagine that most of what we're observing in terms of readily measurable physics, right, is the result of longer timescale stuff where the fast stuff has basically averaged out. Yep. So how do you actually do that in a mathematically consistent way? And this is where the whole beast of ensembles and partition functions and all that good stuff comes to bear, right? And so traditionally, right, although this is not really analytically feasible, you certainly, right, can start talking about partial averaging operators, right? Where if you give me my full Hamiltonian affiliated normalization, which is to say the full partition function or probability distribution, right, for your states, I can just integrate out over the fast and thus effectively project down, right, onto the slow. Right? Now, of course, if that were actually readily doable, there's whole sub-areas of physics that wouldn't exist, right? So this is something that delightfully lives on paper, but does not really necessarily, right, happen in reality. Now, an interesting, and this is a lot of what this work came down to, correspondence, right, with these sort of Hamiltonian formulations of stat mech, is that the Louisville formalism, right, in which we can track the evolution of any observable along my flow in terms of, say, generalized position and momentum, right, is just a linear PDE. That linear PDE, of course, has linear operator L defining it. And if I want to actually then just find a solution, I just find the affiliated semi-group, right, connected to that generator. Well, that's a Koopman operator, right? And in some sense, that was Koopman's initial motivation in putting all of this together. He had this strong background in classical mechanics and stat mech. He was working with von Neumann in problems with quantum mechanics, and he wanted to recast quantum mechanics entirely in terms of linear dynamics. And he was like, well, I don't know how to do that. Do it this way. Yep. So that said, if we want to start doing, right, slow reduced averages, that means we need to kind of take our Koopman operator point of view and merge it with this projection operator point of view. Okay? Get these two things to talk to each other. And if you go look through the non-equilibrium stat mech literature, there were two fellows, Morian 65 and Swanzig in 73, that roughly speaking figured out how to do this. And what's interesting about this is a really natural way to figure out how to get a model for memory into your, right, data modeling or physics or whatever you want to be doing. Where the memory, if you will, is carried by this kernel operator K. So what you're basically doing is taking this simple linear Louisville equation with its simple generator solution, taking your desire for a projection operator, and again, it's all linear at this level, yeah? And then you just kind of cut, paste, shuffle, and move until you get something that's internally consistent. Now, where does the consistency come from? It ultimately gets closed by this being all the scales you can't resolve. So you treat this effectively as a random forcing term that is beyond the reach, in some sense, of the scales you want to project down to, or lives in an orthogonal space. Yeah. And so what's kind of really weird and graceful about this approach is it lets you start building out models for things happening at slow scales, forced by random information at fast or unresolved scales in a way that is completely consistent, right, with whatever underlying model you think your physics is meant to behave overall. What? In some sense, it's almost a kind of ensemble method back again. Except instead of just picking a bunch of random initial conditions, it kind of tells you how to build out random states in a way that's completely consistent with the underlying physics of your problem. It's slick. It's really hard to understand at first, but it is very, very slick. And it's so slick that it caught the imagination in particular of one Alexander Chorin. And if you know Chorin, he might even still be at Berkeley. He was for ages. And he's kind of the father of modern computational fluid dynamics. Yeah, his PhD thesis when he was at NYU in the late 60s is still seminal. And if you really want to read, like, incidentally, they didn't have computer graphics at the time. And so his was one of the first really like successful approaches at solving Navier-Stokes completely on a computer. So it's absolutely legendary work. And he was trying to show that he could capture vortex motion. And so he had to like plot out the vortices as this sequence of X's. And then he like shows how this like 9-bit representation of a vortex in X's like swirls. And it's just like the weirdest plot I have ever seen in a paper, and it's cool as hell. And it's one of those things where, like, if you could even imagine in '67 what we could do now, and it all starts with this goofy little sequence of X's on it. It's just so cool. I digress. Anyway, so he and collaborators in the early aughts looked at this and were like, oh, you know what? You don't need a Hamiltonian here, you just need a dynamical system. And really the question is, there's going to be scales we think we can readily measure, and there's things that we can't get our hands on. And once we have that fundamental dichotomy in mind, right, effectively, they didn't use the term Koopman operator, but they used all the same machinery. So arguably, and this is true of any good idea in the sciences, right, someone always discovers it before the person who discovered it. I mean, that's just absolutely true. Right? I mean, like, look at the wavelet literature. Wavelets were around for generations. It's just no one saw quite how to put it all together, right? Until certain seminal figures came along. And this is absolutely the case here. And this has slowly been gaining ground in a lot of the engineering literature. Because again, if you want to start thinking about trying to use hopefully relatively simple models for your physics, i.e. reduced models, but that also still incorporate unresolved scales in a consistent way, this is the machinery you're going to need to use. And of course, I'm motivated by Koopmania, which is an official term in the literature now. And so I said, okay, let's make this a Koopman problem. Let's say I just have data. I don't have my semigroup. I don't have the Koopman operator, but I know it's out there. How can I do all of this with just data? With the idea then that what I'm going to be able to do is take data that's measured at slow scales, but then consistently include random effects from fast scales in a way that will respect whatever the underlying model is. See what I'm saying? Poor Jay, this is what I started him on for his PhD thesis, and he almost lost his mind. It's weird. It's really weird. So at the end of the day, what we're going to assume, a la what Moraines Wanzig spend all their time worrying about, is how do we get at this projected Koopman operator? Because that's the game. Right? That's what I want. And my time draws nigh. And what I'm about to show you is such a pig's breakfast of perturbation theory. I mean, there's some cute little approximations and some ways that I can start introducing the noise such that it's nice. And then I just geeked the hell out on perturbation theory for page upon page upon page. Yeah, I was so happy when we were doing this. Because it was like years of my formal education in like graduate school finally coming to like fruition on a data problem. And I was like, yeah, they told me this stuff was useless, but it's not. So moral of the story, what we're able to do, and this is really kind of fun, we are able, if not to get directly at our, in some sense, projected Koopman operator, a la the DMD methodology, we are able to figure out what leading order approximations to its eigenvectors and eigenvalues ought to be. And then we're able from there to figure out using effectively ensembles of random perturbations to these problems, what the next order corrections to the spectra and the eigenvectors should be up to linear order in the time step. It's cute, and it's all data driven. So just as a quick test, and this is going to look kind of rinky-dink, but this is what Chorn and company were able to do, so we did it too. We take a relatively straightforward Hamiltonian, a la here. We say we measure the first two directions, and then we just leave the last two as essentially stochastic, something to be averaged over.
In this case, they're not faster, they're just hidden.
Yeah, they're just hidden. So yeah, that actually kind of bugged us a little bit, and we do actually look at a multi-scale problem later, because that just felt a little more legit. You know? And so what's actually slick about this is the measured curve is one realization off of one known set of initial conditions. So I give you one measurement, right? The projected is what would happen if I gave you 10,000 measurements in average. So I give you 10,000 realizations. So I know the initial conditions up to 2 coordinates. I leave the other 2 random. I give you 10,000 realizations of that, and then average. So that's how I get the projected curve. And our whole point here is we are able to get with our, I don't remember what the MD. Thank you. Memory dependent. That's funny. Anyway. Right? We're able to get our memory dependent DMD approximation off of just this one measurement. So we're able to build out an ensemble of perturbations around the measurement, and then off of that in our approximation scheme, get down to something that is pretty damn close, all things considered, right? Especially taking into account how much we don't measure and how much we don't know, right, about our dynamics. Okay. And then I think we start looking at what happens when we crank up the noise. Okay, things get worse, but hey, at least it's somewhat consistent.
No, I don't think you're getting worse. This is actually better. You're just off phase. And phase, you will always lose, you will accrue a loss of phase over time. But if you just displace your 2 curves, I think this is even better approximation than the previous one.
I think so too, honestly. And I think I like gently danced around saying that to the reviewers. Although frankly, weirdly, like this is one of those rare moments where you submit a paper and the reviewers come back and they're like, this is awesome. Like we didn't have to do anything to get this to the review, aside from like, polish up some grammar. It was really nice. So anyway, thanks for sitting through part 2.
All right, let's thank Chris.
Any further questions from Chris?
I have a question. When you were talking earlier about the wavelets that were being used, how did you go about deciding which other wavelets to go about?
Yeah, so we ended up using like Quiflet 4, just because those are very, very smooth and symmetric, and it just made everything seem to play together a little more nicely. But yeah, there's no a priori reason that you had to use those. I tried using lower regularity, options because I thought that might be more reflective of the jaggedness. And that sometimes helped a little bit, but I mean, ultimately, by the time we get everything busted down to those 24-hour averages, that provides so much inherent smoothing from the get-go that actually Quiflet 4 came back around to become the overall better choice. But if I were smarter and knew something about actually building out real adaptive basis style approximations as opposed to just let me hit it with the wavelet hammer that MATLAB provides, you could probably do something more sophisticated, no doubt. But I like orthonormality because I just feel safe there.
Any more questions from Chris, Jay?
I mean, so Jay basically hired me to work with him at ONR this summer, so we'll see. Thanks, boss.
Revenge. All right, so let's thank Chris again for this wonderful talk.